Welcome. Contrary to calculations made by some engineers, bees can fly, dolphins can swim, and geckos can even climb. The challenge, of course, is to answer this question. What permits this extraordinary performance of animals that allow them basically to go anywhere? And if we can figure that out, how can we implement those designs? Well, many biologists will tell engineers and others organisms have millions of years to get it right. They're spectacular. They could do everything wonderfully well. So the answer is biomimicry. Just copy nature directly. We know from working on animals that the truth is that's exactly what you don't want to do. Because the constraints in building any organism, when you look at it, are really severe. Natural technologies have incredible constraints. And this is really important when you begin to look at animals. Instead, we believe you need to be inspired by biology. You need to discover the general principles of nature and then use these analogies when they're advantageous. This is a real challenge to do this because animals, when you start to really look inside them, how they work, appear hopelessly complex. There's no detailed history of their design plans. You can't go look it up anywhere. They have way too many motions for their joints, too many muscles, even the simplest animal we think of, like something like an insect, and they have more neurons and connections than you can imagine. Now, how can you make sense of this? Well, we believed and we hypothesized that one way animals could work simply is if their control of their movements tended to be built into their bodies themselves. What we discovered was that 2, 4, 6, and 8-legged animals all produce the same forces on the ground when they move. They all work like this kangaroo, they bounce. They all produce the pattern of a pogo stick. How is that true? Well, a human, one of your legs, works like 2 legs of a trotting dog, or works like 3 legs together as one of a trotting insect, or 4 legs as one as a trotting crab. And then they alternate in their propulsion. But the patterns are all the same. Of course, they move in the other plane as well. And say, why model just in the sagittal plane or the vertical plane when these animals are moving in the horizontal plane? This was a good question. And we modeled the animals moving in the horizontal plane as well. We took their 3 legs, we collapsed them down as one. We got some of the best mathematicians in the world from Princeton to work on this problem. And we were able to create a model where animals not are only bouncing up and down, but they're also bouncing side to side at the same time. And many organisms fit this kind of pattern. Now, why is this important to have this model? Because it's very interesting. When you take this model and you perturb it, you give it a push. As it bumps into something, it self-stabilizes with no brain or no reflexes, just by the structure alone. It's a beautiful model. Let's look at the mathematics. That's enough. The animals, when you look at them running, appear to be self-stabilizing like this, using basically springy legs. That is, the legs could do computations on their own. The control algorithms, in a sense, are embedded in the form of the animal itself. Why haven't we been more inspired by nature in these kinds of discoveries? Well, I would argue that human technologies are really different from natural technologies. At least they have been so far. Think about the typical kind of robot that you see. Human technologies have tended to be large, flat with right angles, stiff, made of metal. They have rolling devices and axles. There are very few motors, very few sensors. Whereas nature tends to be small and curved, and it bends and twists and has legs instead and appendages, and it has many muscles and many, many sensors. It's a very different design. However, what's changing, what's really exciting, and I'll show you some of that next, is that as human technology takes on more of the characteristics of nature, then nature really can become a much more useful teacher. Let's go to the video and let me show you some of these animals moving, and then some of the simple robots that have been inspired by our discoveries. Here's what some of you did this morning, although you did it outside, not on a treadmill. Here's what we do. This is a death-head cockroach. This is the American cockroach you think you don't have in your kitchen. This is an 8-legged scorpion, 6-legged ant, 44-legged centipede. Now, I said all these animals are sort of working like pogo sticks. They're bouncing along as they move. And you can see that in this ghost crab from the beaches of Panama and North Carolina. It goes up to 4 meters per second when it runs. It actually leaps into the air and has aerial phases when it does it, like a horse. And you'll see it's bouncing here. What we discovered is whether you look at the leg of a human like Richard, or a cockroach, or a crab, or a kangaroo, the relative leg stiffness of that spring is the same for everything we've seen so far. Now, what good are springy legs then? What can they do? Well, we wanted to see if they allowed the animals to have greater stability and maneuverability. So we built a terrain that had obstacles 3 times the hip height of the animal that we looked at. And we were certain they couldn't do this. And here's what they did. That animal ran over it, and it didn't even slow down. It didn't decrease its preferred speed at all. We couldn't believe that it could do this. It said to us that if you could build a robot with very simple springy legs, you could make it as maneuverable as any that's ever been built. Here's the first example of that. This is the Stanford Shape Deposition manufactured robot named Sprawl. It has 6 legs. They're the tuned springy legs. It moves in a gait that an insect uses, and here it is going on the treadmill. Now, what's important about this robot compared to other robots is that it can't see anything, it can't feel anything, it doesn't have a brain, yet it can maneuver over these obstacles without any difficulty whatsoever. It's this technique of building the properties into the form. This is a graduate student. This is what he's doing to his thesis project. Very robust if a graduate student does that to his thesis project. Here's one example that's really exciting. A biologically inspired bouncing robot from the University of Michigan in McGill named Rex for robot hexapod. And this one's autonomous. This is the Rex making its first outing in a demo. Same principle.
Wow.
It only has 6 moving parts, 6 motors, but it has springy, tuned legs. It moves in the gait of the insect. It has the middle leg moving in synchrony with the front and the hind leg on the other side, sort of an alternating tripod, and it can negotiate obstacles, just like the animal.
Oh my God.
You go on different surfaces. Here's sand, although we haven't perfected the feet yet, but I'll talk about that later. Here's Rex entering the woods. Again, this robot can't see anything. It can't feel anything. It has no brain. It's just working with a tuned mechanical system with very simple parts, but inspired from the fundamental dynamics of the animal.
Oh. I love him, Bob.
Here's going down a pathway. I presented this to the Jet Propulsion Lab at NASA, and they said that they had no ability to go down craters to look for ice and life ultimately on Mars. And they said especially with legged robots because they're way too complicated. Nothing can do that. And then I talked next. And I showed them this video with a simple design of Rex here. And just to convince them we should go to Mars in 2011, I tinted the video orange just to give them the sense of being on Mars.
Oh.
Where is this going? I think you can see it already. Clearly, the internet is already having eyes and ears. You have webcams and so forth. But it's going to also have legs and hands. You're going to be able to do programmable work through these kinds of robots so that you can run, fly, and swim anywhere. So in conclusion, I think the message is clear. If you need a message, if nature's not enough, if you care about search and rescue or mine clearance or medicine or the various things we're working on, we must preserve nature's designs. Otherwise, these secrets will be lost forever. Thank you.